Hello, Advanced Calc students. We're in Chapter 8 now, which hopefully for a lot of you is familiar stuff on Taylor series. So a lot of this, especially from Calc 2, should be kind of an easier way to finish the semester. So we're going to do number 4 first, which I'm only going to do 2 of these. 4 says show each series is divergent. Well, on all 4 of them, the terms just don't go to 0. This one is tempting to say that it converges to 0 because it goes like this. And you think they all cancel, but that's not true because remember the partial sums are adding the first 1, adding the first 2, adding the first 3, and so on. And that's the limit of that's what it converges to if it converges for a sum. So if you take this one, you get 1. You take these, you get 0. You take these, you get 1. This is what it means to do a partial sum, right? Add the first few. And it goes like this. And because it never converges, that sequence of partial sums does not converge to a number. This diverges. And you really don't need to go that far. The test for divergence says, hey, these terms that go 1, minus 1 as a sequence, they don't go to 0, so forget it. Similar idea on all of these, really. If you look at C, it's n over the square root of n squared plus 1. If you look at that, whether at a table or as a graph, when n is huge, that 1 doesn't matter, and the square root and the n squared cancel, and you get n over n, which is 1. So however you want to convince yourself, this thing limits to 1. If you look at the graph of the dots, it probably starts out below 1, but it goes like this, and it has a horizontal asymptote of 1. And that's not 0, so this diverges. That's all they're talking about in number 4. 5 gives you a bunch of different things and asks what the sum is. There are only 3 tricks that they're using on all of these. Geometric series, telescoping sums, and adjusting the, I'll call it the starting line. Starting at a later term in the sequence. So I'll try to do 3 of these and see where that takes us. Let me really quickly check which ones change the starting line. Yeah. So I will do C and J. So if you look at C first, it's 2 minus 1 and a half to the n, starting at 0, infinite. Now, actually, we'll just C and D. Generally, the sum for a geometric series is if you have a times r to the n, it'll equal a over 1 minus r. But this is usually starting at n equals 0, which this problem does. For this problem, it's really simple then. It's just 2 over 1 minus a half, which becomes 3 halves. I think you get 4 thirds using that formula. So geometric series are the only ones where we have a very nice, quick, simple formula. Okay, so D is an example of changing the starting line a little bit. And there's a quick way to fix this for geometric series. This one is negative 3/4 to the n, but starting at n equals 1. Okay, so when you write out this expression here, we start normally with 0. It looks like this, a plus ar plus ar squared plus it goes on forever. So what you need is you need the ratio, the r, and you need a, but a is always the first term. So you can play with indices all you want, but it's really simpler if you just write the numbers out. The first term is minus 3/4, and then the next term is negative 3/4 squared, and then negative 3/4 cubed. And that seems like kind of obvious, but that ratio then is negative 3/4. When you write this out, a is always the first term. So when you look here, a is usually the coefficient. You might think a is 1. That would be if you started at 0. Like up here, this would be, a was 2. But what a is always just the first term that you write. Think of the sum another way. You could write minus 3/4, pull 1 out, minus 3/4 to the n, and start at 0. But that's a lot of playing with indices to get the same thing. So just write out the terms. The very first thing you see is a, and then your multiplier is r. So this is minus 3/4 over 1 minus 3/4. And so you get 7/4 on bottom. Cancel the 4s, and I think you get negative 3 7ths. Yeah. Okay, so that's an example of changing the starting line. I'm a little bit out of space, so let's go to another sheet. But let's do J, and here we're going to do telescoping, and we're going to change the starting line. So if you look at J, it's 1 over n times n plus 1. And a lot of these that look like partial fractions problems, they basically are. This problem starts at n equals 5. So there was a practice problem in the paper, in the text, starting at n equals 1 or 0 for this, or probably n equals 1. So, but let's do this. If you don't remember how to do partial fractions, which really I guess is what you have to do here, this should be a over n plus b over n plus 1. You multiply across by the denominator to get rid of it, and then you're going to use elimination after this point. So if you make n 0, then 1 becomes a. If you make n minus 1, 1 is negative b. So a is 1, b is minus 1, and so that means this expression at the beginning is really the same as 1 over n minus 1 over n plus 1. And now you're going to see that this is telescopes when I write it out. So let's take this thing, we write it again down here, now that I've separated it. So partial fractions is the most common trick to set up telescoping, especially if it looks like a rational function, a ratio of polynomials. So let's start at n equals 5, and then plus 1 over 6 minus 1 over 7. And you can see that these are going to cancel, and it makes you think the answer is 1/5, but let's be careful. Let's write down the first partial sum is 1/5 minus 1/6. Second partial sum is 1/5 minus 1/7 after you cancel those. The nth partial sum should be 1/5 minus, I guess 1 over n plus 1. And as n goes to infinity, the Sn goes to, well, that goes away, and you get 1/5 as the sum for the answer. Alright, so that's how you do telescoping sums. So those were 4 and 5. Next problem is 9. 9 says determine whether or not a particular series converges and gives your answer. So I'm going to write down that series. And it is this guy. This again makes me think of telescoping sums, because you have the plus here and you have the one index and the next. And square roots on bottom should make you think about conjugates, so make sure you change it to a minus sign. So multiply across here. 9. The bottom you get n plus 1 minus n, which cancels. And now you get that. So now let's write out the telescoping. You get square root of 2 minus square root 1 plus square root 3 minus square root 2. But I think this diverges in terms of the telescoping, because this cancels, but the stuff that doesn't cancel grows. So your first partial sum would be this. Your second partial sum would be this, and I think your nth partial sum would be this. And because as n goes to infinity, as n goes to infinity, that diverges, even though the terms go to 0 at the start, right? Just because the terms go to 0 doesn't mean that it converges. Harmonic series is the standard example. Okay, so that was number 9. Now I want to do 12 and 13. Okay. So you got a sequence of positive numbers, and we're going to average them and show that it's still, that it's going to diverge. Okay, so we have a sequence of positive numbers, and I want to take Bn to be the average of the nth numbers. Doesn't even matter what they are, they're just positive. And we want to show that Bn diverges to plus infinity. Okay, well, I don't really know how to do this other than to try the partial sums. So let's try that. So a partial sum would be up to an nth spot, the SNs like I was doing before. So we need a dummy subscript in the meantime, so let's use K. So this is the first BNs. And now let's write out what those are. This is A1, 1 plus A1 plus A2 over 2 plus A1, A2, A3 over 3. And then the last one is A1 through Bn over n. And what you should hopefully see is you can kind of see the harmonic series showing up. If you think about, all these things are positive. Look at just the A1s. This is greater than or equal to A1 and then 1 plus a half plus. You got all the other stuff that I'm not even using, but this is the divergent harmonic series to plus infinity. So some scalar multiple, A1 is a fixed positive number, will still diverge. So this is also the comparison test. So 1 over n diverges, multiplying by a positive constant, it still diverges. So it diverges by the comparison test. Okay. 13. We're going to skip 13. 13 is interesting, but I'm tired of beating over the head with stuff. So we're going to stop there, and you guys can skip 13.